So when I write kinetics of particles, again I have another part, kinetics of rigid bodies, which we will go into that later. But now when I say kinetics of particles, it is only translational study. Effect is what is translation alone. Translation alone, right? So what is the fundamental equation that governs this translation is a body can be, this is a rigid body, it is subjected to n number of forces, say F1, F2 and so on, Fn. So I will have some resultant force, and that would be equal to, if this is a body CG location, that would undergo a motion by the effect force m into a. So that's mass times acceleration. So this is what is Newton's second law, and you have an unbalanced force present in that. I ignore the physical geometry. So physical geometry is neglected. Then what will happen? Though the application of point of forces are different location in a rigid body, all become concurrent system. So I will have my unbalanced resultant force, and this body is not constrained at all. So it will be undergoing motion in the direction of resultant, and this what is called an effect force. Effect force. So unbalanced resultant is equal to effect force is what is given by Newton's second law. Right. So we are going to apply this law, and we are going to solve problems now. And you can also see in textbook the Newton's second law is also other way represented by D'Alembert's principle. What do you mean by D'Alembert's principle? Looking at the body which is about to start its accelerated motion, or looking at the body which is about to stop its accelerated motion. That wedge, if you look at, you see that this effect force is an inertia force which is added with this resultant unbalanced force, so that it is balanced and made equal to zero. So that's what is D'Alembert's principle. So unbalanced resultant plus the inertia vector, which is ma, that's equal to 0, is what is D'Alembert's principle. So what do you mean by that? There is a resistance by virtue of the mass of this body. So that would be mass times acceleration vector, which would try to oppose. So I try to push a heavy load, which is trying to oppose initially, but it is overcome, and that is what is set into accelerated motion. So if I look at just to start the motion state, then unbalanced force plus this effect force is otherwise called an inertia force in that scenario, and that is added with this, it becomes 0. So this inertia force minus sign is referring, it is a resistance. So this is added with this unbalanced force equal to 0 is what is called a dynamic equilibrium. You can see textbook dealing with the dynamic equilibrium of every kinetics of particle problems, and you can solve. Or you see classical textbook like Beer and Johnson, other R.C. Hibner and so on, deals with looking at free body diagram where you get all the active and reactive forces. It's unbalanced forces, and then you get that's equal to an effect force, which is accelerated force. And you have two diagrams. One is called the kinetic diagram, and that is in this side. Another one is what is called a free body diagram, that is on this side, FBD. So whatever FBD that you have drawn and statics, the same you will draw here, removing the support, showing the reactions and all active forces, and that is what is made equal to effect force, and that is what is called the kinetic diagram. So one can have this approach of solving problem or this approach of solving problem of this group of kinetics part of rigid body mechanics. So I'm going to take some example problem today to confirm this application of this Newton's second law, right? So let's take an example problem first. So I'm going to look at now a system, describing you the system. So I have here a point where I have a bucket filled with water. So this is full of water. Bucket filled with water. It's tied with the string, and the string is now swinging. It is going around this vertical axis, swinging. It goes so that this will follow a circular path. So this go around a circular path. So it's very clear to understand. So now this orientation is given by 35 degrees. So this is an inextensible string, and one end of the string is tied here, other end is with the bucket filled with water, and this bucket is now whirling around this axis, and bucket goes in a circular path. And now what's happening here, this bucket now has got a small hole, and that is why there is this slippage, that water is dropping out of this bucket. So water drop comes out of this bucket as this is going with a rotational speed, right? It is going with the velocity. So the linear velocity of the bucket, if you see, it is tangential at that every instant on this circle. So that water drops follow a path that comes out, falls on the ground, and it makes an impression in the ground. So that is this impression. There is another circle created, and that is an impression made on the ground. So now let us look at the height of this ground from the point where this is tied is 4 meters. And the length of this cable till this point is what is given by 1.5 meters. So the circle is now from this top till this point, what is the distance that you know? So if you see this is a projection in the front view, I will have this is going to be drawn something like this, something like this. So here is the bucket, and this distance is the radius of the circle. So the circle will appear like this. This is the circle in orthographic condition. A triangle, when I view this is the pictorial diagram. So this bucket goes in a circular path, and the circular path is horizontal. It's parallel to the ground. And I have here again an impression in the ground. Impression in the ground, maybe that's here, down. So this is of 1.5 meters. So this angle is 35 degrees. Now this distance is 4 meters now. So I have here another circle, right? So now what is the radius of this circle is the question. What is the radius of the circle? That you have to find out. So I have posed the problem. What is the problem statement? A bucket which is tied on one end of the string, where the string is whirling around this vertical axis. That instant that orientation is 35 degrees. The water drops comes out of this bucket because of small hole, tiny hole present there, and that water drop comes out continuously. We are looking at shortest instant duration, so that we can neglect that mass variation in this bucket. We assume that bucket mass is same. We know that it's a bucket without hole, that mass that bucket is that occupied by the water. But now small hole is there, water comes out. We look at the smallest duration where the drop of water comes out. That mass compared to that of the total mass of water, you can neglect it, so that you can assume this weight of the bucket is same. And it goes in this path, the circular path, and the water drops falls on the ground will make another impression on the ground. That is a circular impression. And what is the radius of this circular impression is the question. So this is what is the question. So how do you go about finding out? right? So that is the question. So any doubt in this question? Anybody? So anybody has got a doubt in this question? If you do not have a doubt in this question, let me explain you how do you go about solving this problem. So now what is the way to solve this problem? See, the question is here, determine what is the radius R, or the impression made by water drop. This is an impression made by water drops on ground. So that you have to find out the radius of that. So how do you find out? Look at now water drop. This problem has to be looked at so carefully. It's a very interesting problem. I know that the water drop comes out of this bucket. Bucket goes in a path. I know it's a geometry of motion. What is the geometry of motion of a bucket? It is curvilinear translation. So the bucket goes in a circular path. The radius of the circle is fixed. So what is that? It is 1.5 meter, and this orientation is this. So this should be, you would say that it is 1.5 sine 35 degrees. What is this height? So you would be able to say that this should be 1.5 cos 35 degrees. And then what is this distance from here to here? You would be able to say that it is 4 minus 1.5 cos 35 degrees. So this all are what is given data and your further inference of the given data. So now water drops comes out of this bucket. What is its velocity? If I know, I would try to find out the kinematics, through kinematics, the motion geometry of the water drop that makes the impression on the ground. So as this goes, what is the velocity of the bucket? I can find out from kinetics, right? That's first step. So how do I get the velocity of the bucket from kinetics? What is that I require? I require what is the acceleration of this bucket. I need to find out. If I know acceleration of this bucket, and in the horizontal plane, in the top view, if I see this, so what is that I have? I have it here, two circles in the top view. One is the circle impression made by the path of the bucket. So that's this circle, this project. So another one is the path of the water, the impression made by the water droplet. That is this circle. It's a concentric circle now. Two circle. So what is now asked is this circle radius is what is asked. So we know now this circle is what is the path of the bucket, and this circle radius we have to find out. So now how do I have an approach of finding out this? Find the acceleration of this bucket so that I can resolve that acceleration into two components. One is centripetal component, another one is tangential component. And you are given here, this bucket is rotating with a constant speed. That's a statement additionally given. So let me read the statement of the problem. A bucket filled with water is tied to a 1.5 meter long inextensible string. Is whirled such that the string makes an angle 35 degrees with the vertical as the bucket revolves with the constant speed. Bucket revolves with the constant speed. That means the V, the tangential velocity of this, bucket at any point, if you look at, that's constant, right? So that's going to be R times omega in a horizontal string. So this V is constant. So when I say V is constant, is this bucket undergoing accelerated motion? Is my question. You should answer that yes.
Yes, sir.
Why? Because it is going in a circular path. So you will,
because of its centripetal acceleration.
Yeah. So if you are able to get your centripetal acceleration, you know that is relating to this velocity by this v squared by rho. So I know what is my velocity of the bucket. So knowing velocity of the bucket, I know whatever the water drop comes out of it, its velocity. So that is going to have its velocity in the same direction as that of the bucket. And that is its initial velocity, and that water drop will come and hit the ground in a path called parabolic path, as the air resistance in this condition is neglected. So if you look at this, comes out and it will go. So if I see at this position water drops comes out, how do I represent in this diagram is, this is the point. So the water drop of that one drop will go in a projectile path. So it is a path, and it will go and hit at this point. So next drop, as it comes, it will hit. That is how you get it. So this tangent drawn for this path can be many tangents as it completes one circle. So every tangent hits this ground in a path followed is a parabolic path. So what is this now? If this is point A and this is point B, so AB on the ground, AB on the ground would be this point projected here. So this is A, and here is the point. AB on the ground is what is the range in the projectile motion, whereas you see this height is what is that path it is followed, right? So I will be able to solve this problem looking at the path of the water drop. So let me draw path of the water drop in this fashion. So when I look at that in a side view, I would be able to see that it follows a parabolic path and comes and hits this ground here. So this is the ground level. So now what is this height is known. So this is point this is the point where water drops comes out with a velocity which is the same as that of velocity of bucket, and this is the height, vertical height, it is translated and to reach the ground. So this point is the center of the ground, and this is point B. So let me call this point as A, this point as B, and this comes here. So what do I require is this distance x is what I require, which I can find out from the kinematics. The kinematics of projectile motion. Where is it? Projectile motion. Right? So I have four equations there. So horizontal direction velocity will not change. If you look at, this is the velocity of the water drop, and that would be same here, same here, same here. The velocity remains same horizontal, but vertical component here, zero velocity is going to be increasing. So that the resultant of these two, if I look at, that would be tangential at this point. So resultant of this, if I look at, that would be tangential here. That's tangential here. Right. So this is what is that actually what's happening with the kinematics of water droplet path. So like that, n number of water droplets comes out in one circle motion of a bucket. That creates a circle impression. So that's what is our question, and we look at that one circle made by a bucket and corresponding impression on the ground by the water drops. So if that is so, and we will have to find out this x now. How do you get this x in the picture now in this diagram? That is exactly by this. So this is x. So if I have x here, and I know this is small radius of the path r, and I can find out now what is this capital R. So this capital R I can find out. All right. So let me edit this. So this is the capital R, which is this radius I can find out from this right angle triangle. So I know this R already from the given problem statement, that is 1.5 sine 35 degrees, and I can find out what is x if I know my velocity of water drop. I can find this. If I know this is a right angle triangle, so I can simply get what is this R. So this R is now under root of small r squared plus x squared, as simple as that. So now the task is to find what is this x. To get that x, I require what is the velocity of water drop, this velocity. So to get that velocity, I should now find out the acceleration of the bucket. So to get an acceleration of the bucket, I should draw the free body diagram of the bucket. So I had to applying Newton's law to the motion of bucket. Applying Newton's second law to the motion of the bucket. Motion of the bucket. So what is that? I have here now, this is a bucket. And I know it's weighing W times that's mass times G, its weight, and this orientation is 35 degrees, and that's equal to its acceleration effect diagram. This effect diagram. So this is the circular path. So in this, you will see that you'll have my acceleration here, an component and at component, and that's equal to 0 as v is constant given. So now an component I have to find out, right? So here what is that my free body diagram, W, and I cut this, so the tension here, tension in the bucket. So what is the weight of this bucket? So you are given the weight of this bucket in the problem. It is not given, it is needed. It is also not needed because I require now to calculate what is an, and that is in this direction. So if I consider my direction x and this is y vertical, so in x direction, what are my forces? W is vertically acting down. So I know what is the tension in this cable. So that is going to give me in related to weight. But centripetal acceleration in the plane, which is at right angle to that. So my application of Newton's law in x direction, that is sigma fx equals man. So if I consider this is positive and this is in the negative direction, so I have to put here it's minus. So now what is my fx? That is this. So this angle is 35, this angle is 35. So horizontal component is minus t opposite. So sine 35. That's equal to minus man. And looking at the sigma fy equal to may. There is no acceleration in vertical direction because it goes in the horizontal plane. So bucket is not going above. So there is no acceleration. So that is 0 here. Sigma fy equal to 0. That is what is going to be t cos 35 minus w, that's equal to 0. So now what is t cos 35? That is w. So I can write it as m times g. So I can put what is t now as mg by cos 35. So this t I can substitute here. So it is mg sine 35 by cos 35 equals minus m into an. Sorry, plus this goes off. So I get an as 9.81 into tan 35. So what is the value that I get? What is the value that I get?
6.861, sir.
6.8? 6. Yeah. So,
Sir,
yeah. 9.81.
sir, how do you minus f, sir?
1 minute. And 0.869 per second square. Yeah, what is the doubt?
So just calculation part, sir. Sigma fx, sir.
sigma fx.
Yes,
So
sir.
look at now, I look at now only the horizontal plane. So this goes in a circular path, right?
Okay.
Like that. So now, if I resolve this force in the vertical plane and horizontal line here, so I just apply this equation, sigma fx equal to MAN, because the MAN is what is your centripetal acceleration, which is horizontal, and this tension and weight, tension is now inclined to vertical, so I know what is its horizontal component, but weight is acting vertically down. So when I have to apply my Newton's law, I apply along x direction and along y direction. When I apply along x direction, it is sigma fx equal to MAN. So why do I put minus MAN here? Because I know that this is, if I consider this is positive direction to the right, AN is to the left, so that's why I put here minus. And sigma fx, when I write T, I am just resolving now in this direction. That's going to be T sine 35. And to the left. So I can resolve this T as T sine 35 and T cos 35. So T cos 35 balances weight, T sin 35 balances my centripetal acceleration. That's what I put it here. And tension value to be substituted. So I use that equation applied in vertical direction. And bucket is not going vertically up. It is in a horizontal plane rotating. So acceleration in vertical direction is 0. That's why sigma Fi equal to 0. And these are the two forces in vertical direction, that is T cos 35 and W equal minus W equals 0. So I get T, and substituting this, I get this. So this is my centripetal acceleration, and that's what is equal to V squared by rho. So now I can find what is the velocity of my bucket. So as AN is equal to V squared by rho is found out, I can find now V equals under root of AN into rho. So what is the AN? Just now we calculated 6.869 multiplied by rho is the radius of the circular path of the bucket. So radius is 1.5 sine 35. So working out for this, I get 1.5 into sine 35 under root equals 2.431. So 2.431 meter per second. So that's the velocity, and this velocity is tangential. So this velocity is tangential. That's what you should see. If this is that inextensible cable, and here is the bucket, velocity is in the tangential direction. So this is the direction V. So this is known now. So this is the initial velocity of water drop. So if I know that the initial velocity of water drop, then I take that looking at from the side view, I just follow that path and till it hits the ground. So this distance is known, that's 4 minus 1.5 cos 45, sorry, cos 35, I'm sorry, cos 35. And I need to find this distance x. So that I can find out from the projectile motion. So now what is the velocity of water drop? It follows in this path. So this is the velocity, and that velocity is same as that of the bucket velocity. So 2.431 meter per second. I know initial velocity now. I can find out now this x, simply the range. So what are the governing equation by kinematics? I have one is the horizontal motion, another one is the vertical motion. So horizontal component, horizontal motion if I consider, so that's going to be x equal to vt, as x naught equals 0 that I consider, and this is my reference point 0, 0. Please mute, there is a noise from your end. Mute for all. But Sajal Karna is audio is creating some noise. Sajal, you have any doubt? So now we
Excuse me,
have,
sir.
yeah,
So in the initial question also you said some velocity of the bucket is given, right?
where is it given? I said you have to find out. If it is known, then you can. You have missed my statements, what I made. Initial velocity of the bucket to be found out.
Yes, sir, we did, sir. I thought you in the
I,
starting only you said in the question when you were saying the
yeah,
velocity of
initial
buckets given.
velocity of the bucket is no with the constant speed. That's what I was telling. It goes with the constant speed. Our point of observation, the velocity of the bucket is constant. If you look at what I discussed, if you miss out, no, it will confuse
No,
for
no,
us.
sir, I didn't miss out, sir.
Yeah, you look at here, I was marking these statements here. So the velocity will be always tangential, and that will
Yes,
be
sir.
obtained from rho times omega. So how do you get this?
Sir, from this thing, sir.
From here, centripetal acceleration velocity, right?
Yes, sir.
Yeah, there is no
Yes, sir.
rotation.
Okay, sir.
This is maybe misguided you. So here you have an is equal to v squared by rho. So you will be able to relate this velocity here. There is no angular velocity. I'm sorry. So angular velocity is for if I consider
Rotation effect.
everything is rotating like that. Bucket and
Yes.
this entire plane is rotating, right? So that's constant. That's what is constant given. So any point on this, if we take, that's constant velocity. That velocity is relating with an acceleration of the bucket. So if you find the acceleration of the bucket from kinetics, you will be able to solve this problem, right? Yeah. So you have it now here. This is one equation. So in this, I know now this velocity is constant. So if I know what is the time it takes to hit this, I will be able to find what is my x. Because I know x, I will solve the problem. So now how do I find this time? For that, I will go for my vertical motion. Vertical motion of this projectile. So vertical motion is motion under gravity. So I need to find the time it takes to hit this ground. So the distance traveled vertically is 4 minus 1.5 cos 35. So I know the distance traveled. I can find time from the primary motion equation. X is equal to function of time. So that would be expressed as y minus y naught equals v naught, that is Vy naught t minus half g t square or plus half a t square. So here I put plus sign because the water droplet comes initially tangentially comes out of the bucket, but it gains your velocity. So any point if I take, I see there is a vertical component grows. So that's what is happening. That is how it is bringing the tangential velocity all the time. So initial velocity in vertical direction is zero, but as it hits the ground, it will have a maximum velocity in vertical direction. So Vy naught t is zero here. And since this velocity in vertical direction increases, it is motion under gravity, accelerated motion. And y naught is 0, so it's y. So y is this distance, and what is it? This is my reference. So what is that I should take here? It is minus of this distance. So minus of 4.4 minus 4 minus 1.5 into cos 35. That's 2.77, and 2.77, how should I take? I should take it as, if this is my reference point, I should take that as negative sign 2.771. And here I have half into 9.81 into t square. So this would solve for this minus sign. There is a,
So minus half gt square, sir.
what is it?
Minus half gt square. Acceleration, sir. Negative direction, huh?
Yeah. Um, yeah. Yeah. So this is minus here, yeah, right. So this is going to give you time t equals if I solve this, it gives me 0.7516 second. Right, I take a positive value of this. So now if I have this t, then I'll have my x will be Vt. So V is 2.431 multiplied by 0.57516. So into 2.531, that's giving me 1.827. 1.827 meters. That's x. So I have this x. Then I can find out what is my r. So r is simply, I have this circle represent the path of the bucket. I have a concentric circle which represent the impression made by the water drop. So what is asked in the question is this r is asked. And I know what is this small r. I have just found what is this x. So this x is what is that we are weaving from here, and that's the diagram here. When I weave from here, what is that appears is this, from the bucket it comes out this line. What is x is what is now this range. So it's projected in the top view, and you have this. So from the side view you are able to see, right? So now I have x and r, small r, so I can find what is this r. This forms a right angle triangle. So r will be under root of this. So what is small r? Small r is 1.5 sine 35 degrees. So that's equal to sine 35 degrees. 1.5 into sine 35. That's 0.86 meter. So I have to put that 0.86 square plus 1.827 square, and I'll get R plus 1.827 square. So 4.08 under root equals 2.019 meters. What is the radius? So like this you can solve. So this problems we are using kinematic equation as well as kinetic equation. So what is important in this problem is the statement of the problem says that no geometry prediction appears. So you are given this is going with the constant velocity, the water drops comes out of that, creates an impression in that. So that's all physically the description you are able to follow. To find out this R, how do you go about is finding out the velocity of the water drop, because you know the path of that is parabolic path. And to get the velocity, you should immediately connect. There are no velocity data given in the problem. So you need to connect that with an acceleration. And because the path followed by the bucket is circular path, so you will be able to find what is your AN, and that solves for your V, and that is what is the input for the kinematic analysis of the water drop path. And that's how you have solved this problem now. So with that, let me go with the second problem.